Vibrational motion is considered in this course using a harmonic oscillator approximation, in which the potential energy V, as a function of internuclear separation R, is a parabola. The allowed energies of the harmonic oscillator are energy is equal to a quantum number L plus a half times Planck's constant H times nu, the frequency of the bond. This is proportional to the bond force constant. In this model, the characteristic temperature is h nu divided by kb. The harmonic oscillator model is a good description of small motions around the equilibrium bond length. It's also useful for us as it leads to equations for partition functions and other quantities that are exact. That is, we get equations that do not require further approximations like high temperatures, as translations and rotations do. These derivations and equations on the next few slides are not examinable. We use them to give us another insight into energy and heat capacity of molecular systems. This model gives an expression for the vibrational partition function in terms of vibrational frequency or characteristic temperature. For an oscillator with a characteristic temperature of 200 Kelvin, the partition function plotted versus temperature looks like this. Notice that the partition function goes to 1 as temperature approaches 0, and then starts to increase about when the temperature approaches the characteristic temperature. We can also see how the occupation probability of ground and excited states, I equals 0, 1, 2, 3, etc., change with temperature. Below the characteristic temperature, at 100 Kelvin, the probability of occupation of state 1 divided by that of state 0 is only about 0.14, and the higher energy states are hardly occupied at all. Here Q is near 1 and only one state is significantly occupied. A bit above theta, at 251 Kelvin, the probability of occupation of state 1 divided by that of state 0 is around 0.45, and both the second and third excited states are occupied to some extent, and Q is around 2. Far above theta, at 1000 Kelvin, many excited states are significantly occupied, and the partition function is now much greater than 1. We've already derived an expression for obtaining the total energy of a system of molecules from the partition function, which we can combine with the partition function equation to calculate the total vibrational energy as a function of temperature. The first term is the ground state energy, and the second one comes from the energy of molecules in excited states. For 1 mole of molecules with the same 200 K characteristic temperature, the vibrational energy above the ground state, or 0 point energy, Avogadro's constant times epsilon 0, looks like this. As the temperature goes to 0, all the molecules go to the ground state, and the total energy goes to Avogadro's constant times the ground state energy, which is 0 on this plot. As temperature increases, not much happens to the total energy until we get to near the characteristic temperature, and then the excited state starts to get significantly populated. You can see the change in population from below the characteristic temperature to above the characteristic temperature. From this expression for the total energy of the system, we can calculate the temperature dependence of the vibrational heat capacity. For 1 mole, again, N equals Avogadro's constant, and this looks like this. Heat capacity is the derivative of energy with temperature, so it goes from 0 below the characteristic temperature to a constant value above the characteristic temperature, just like the gradient of the energy graph. At temperatures above the characteristic temperature, the molar heat capacity approaches a value of R equals 8.314 joules per Kelvin per mole. You obtain the same result as this by taking the high temperature limit of the full expression for heat capacity, which is the way that we did it in lecture 5. This curve describes how heat capacity changes with temperature as vibrational energy levels become thermally accessible above the characteristic temperature, allowing the molecules in the system to absorb energy by exciting vibrational transitions. Just as we saw with the partition function, heat capacity changes from T below the characteristic temperature to T above the characteristic temperature. In week 2, we built up partition function expressions for different degrees of freedom, starting with monatomic gases, which have only translational degrees of freedom, then adding in vibrational and rotational motion of diatomic gases, which could be generalized to polyatomic molecules. There is a separate interesting situation that occurs with crystalline solids. atoms or molecules in crystalline solids, from solid argon through to metals, cannot undergo translational or rotational motion. Their only degree of freedom is vibration. However, unlike diatomic molecules, they can vibrate about their lattice positions in the X, the Y, or the Z direction. So they have 3 degrees of vibrational freedom. N vibrating atoms thus gives rise to 3N oscillations. Their molar heat capacities are similar to the vibrational heat capacities of diatomic molecules. They're strongly temperature dependent, rising from 0, near 0 Kelvin, to plateau at a high temperature limit of 3 times the gas constant, if this is reached before they melt, that is. Notice that this old data set uses calories rather than joules for temperature and still uses the old notation of degrees Kelvin for Kelvin. The difference between the temperature dependence of the molar heat capacities of different materials is all a result of the bond strengths, and hence vibrational frequency of the lattice nu. As with diatomic molecules, we can calculate a characteristic temperature for each lattice. The characteristic temperature for vibration is again Planck's constant times the vibrational frequency divided by Boltzmann's constant. If we scale or divide the temperature by the characteristic temperature on the x-axis, this brings all the molar heat capacity data onto a single curve that asymptotes to 3R equals 24.94 joules per Kelvin per mole. This model was originally proposed by Einstein in 1907.